Powerful collaborations, cutting-edge science, and curious minds coming together for a glimpse of the future. Stay tuned as we look at the latest updates on some of the most promising technology projects. Hello and welcome. I'm Peter Ballant from Technicon, and today we look at the FutureTPM project once again. The last time we learned that this project is addressing the elephant in the room. What happens when the really fast computers of the future have the ability to break all the cryptographic security we have in place today? We are talking about quantum computers, of course. Computationally, they are exponentially faster than anything we know, and they are coming, for sure. The FutureTPM project is the proactive approach to ensuring our security standards stand up to quantum computing. And to be even more specific, the consortium is paving the way to the Quantum Resistant Trusted Platform Module, or QRTPM. Today we are joined by Li Chen, professor in secure systems at the University of Surrey. She is the technical lead in FutureTPM. Thanks for taking the time to be with us today.
Thank you. Thanks for having me here. I'm pleased to talk to you about our project.
The Trusted Platform Module, or TPM, is at the center of your project, Li.
Yeah.
Let's start with learning more about the TPM. What does it do? Where do we find it?
This is a good question to start. A TPM is a small chip which is tamper resistant. There are different ways to say what is the chip. Cryptographers probably say this is a cryptographic coprocessor, and engineers probably say this is a security anchor. And TCG, who developed the specification of TPM, will say this is a root of trust.
And you say TCG. What does that stand for?
Oh, TCG stands for Trusted Computing Group. This is an industry standard body. So many computer industry companies are the member.
Okay, and did the Trusted Computing Group sort of come up with the original TPM?
Yeah, they are the developer of TPM specifications. They have been there for many years, since 1999. In 1999, it's not called the TCG. It's called a different name. In 2003, they changed the name to TCG, and they have more and more members.
Okay, and so the TCG would call the TPM a root of trust. Basically, what this means is that a TPM is, in simple terms, a piece of hardware that works to secure a computer, whether it's a personal computer or a part of a server cluster.
Yeah, this is the original design goal. A TPM currently is embedded in many computer platforms. Based on the TCG message, TPM is installed in probably over 1 billion computer platforms, including many PCs. Probably most of PCs have TPM, and some servers, network switches, and a lot of different platforms. Actually, a TPM now is just a set of functions. It's not even necessarily a hardware chip. From TCG's point of view, a TPM is not restricted to be a hardware chip. It could be implemented in a different way, like an integrated TPM, a firmware TPM, a virtual machine environment of TPM, and a software TPM. Although different type of TPM will provide different levels of tamper resistance.
From what you just said, it sounds like TPM is everywhere.
Yeah.
And that's good. This is a good thing. But there's also a challenge for TPM, and that is the fact that somewhere down the road, we will be exposed to quantum computing. Quantum computing will enter our realm. And quantum computing, for the people that don't know it, is to keep things really basic, it's just a really, really, really super powerful computer that could do something in 10 minutes that previously took 5 years, for example. This means that the security that we use today, and we're talking about the TPM here, when quantum computing comes, may not be so effective anymore. Do we have the basic concept correct here?
Yes. Quantum computers, because they can do the parallel computation and they have faster searching, and also they can particularly solve some mathematics problems which are difficulty for the conventional computers. So today, those problems, in particular, I mean, two problems we used everywhere is a factorization problem and the discrete logarithm problem. Those two problems are the foundation for many common used asymmetric cryptographic algorithms, like asymmetric encryption, digital signatures, which TPM use as well. So because a larger scale quantum computer can solve those problems, so those asymmetric encryptions and digital signature algorithms were no longer safe with quantum computers attack. So that's why we need changing this situation. We need to add quantum resistant algorithms into TPM, which are not based on those two mathematics problems, based on some other problems which we believe quantum computer cannot attack, at least for many years.
And so the idea of FutureTPM was to at least start thinking about design to create quantum resistant TPMs. And this project is done at the end of the year. So can you tell me, have you achieved your goals? What's the current status of the quantum resistant TPM?
Yes or no? Yeah, we have developed and identified a set of quantum resistant cryptographic algorithms. We believe as those sets of algorithms, they are suitable for inclusion in a future TPM. Not all of them were designed by ourselves. We followed NIST, which is a standard body, their post-quantum cryptographic standardization activities. So we followed their activities. So we took some result from them. And we also designed some algorithms which is not NIST covered. We have implemented those algorithms and tested their performance. We also have talked to TCG about our result. So in one side, we are ready to recommend something to be included in FutureTPM. But this research is not the end yet. We are still carry on doing it, try to improve algorithms and their implementations to make the performance is better. It's not a complete finished. Our goal is still ongoing.
Right. I would imagine this would take quite a bit of time to actually get this to the point where you really have a quantum resistant TPM. But this is a good start, the way it sounds. And especially because of the fact that you mentioned that you talk with the TCG about some of your results. And this is an important thing for you. Tell us what this means for the project, that you got the recognition of the TCG.
Yes. Because our project is about future TPM, and the TPM specifications are developed by TCG, and the TCG actually own the technology of TPM. So if we want to recommend some algorithms to be included in a future TPM, we have to go through TCG, that's for sure. And actually, we have very good collaborations with TCG start from day one, because number one, we have a number of core TCG members, they actually in our consortium. So we are not isolated from TCG. And also we have TCG Technical Committee Chairman, we have TPM Working Group Chairman. They are our member of advisory board. So TCG actually involved in our project from beginning. And recently we have arranged a meeting with TPM working group with TCG members to introduce our result. And they are happy to hear this. And our working relationship with TCG has been doing very well.
And that's great news for the project, for the FutureTPM project.
Yeah.
It's also great news for some of the research that's happening here in Europe.
Yeah, that's true. Yeah, Europe play a very important role in the information security technology, trusted computing technologies. Yes, it's certainly good for Europe, and Europe also is a big market for the TPMs.
Yeah, absolutely. Lee, I wanted to go back to something we talked about a few minutes ago, which was the idea of quantum computing. For many people listening, this may be a new concept that they haven't heard before. And the question they might be asking is, what kind of threat is this? How long do we have? When is this coming? Maybe you could put things in perspective about when should we anticipate the entrance of quantum computing into our day-to-day life?
Well, we actually don't know for sure when a quantum computer, I mean the largest scale quantum computers, will become a reality. Although we have small quantum computers with a limited number of cubicles, we already know that. But for the quantum computer be able to break the crypto algorithms we are commonly use is a different things. When they will be available, no one can say for sure. But the things we need to do is we have to prepare a smooth transitions from today's crypto solution to tomorrow. We cannot wait until a quantum computer coming out. Some people predict, say, the quantum computer will coming in 15 years or 20 years. But we cannot waiting for 15 years or 20 years to start our research. We have to make a quantum resistor TPM ready before the time coming. So by the smooth transition, I mean this transition should not affect most of TPM applications. We need to make those applications be able to carry on before quantum computer coming out or after. So actually, for this FutureTPM project, we said we are going to design and develop a quantum resistant TPM, but we actually not try to design a new TPM from scratch. We try to identify those suitable quantum resistant crypto algorithms for FutureTPM, and we are going to add in those algorithms in the TPM algorithm registry and to make it ready for the quantum computer coming out.
And this makes much more sense. Rather than developing something from new, you're taking what's existing and just doing what you have to do to make sure that it works in the quantum computing world. Yeah, it makes perfect sense. And it seems like that if, for example, this does not happen, and if quantum computing then can find a way to break the security that we're used to today, that we enjoy, this means everything could be at risk here. Medical records, authentication credentials, financial and banking data. So the impact of a quantum-resistant TPM could be quite profound.
That's true, yeah. For data protection, and currently many platforms use TPM. For example, like Microsoft used TPM to make a 4-disk encryption, which is called BitLock, and also many other manufacturers use TPM for a different service, like the attestation service, which is typical TPM functionalities to support the platforms be able to communicate to each other safely and to check the trustworthiness of their communication partners. Yeah, this is all very relevant and important to the world.
Ali, I want to ask you about the consortium a little bit. Like any other European project, this is not done by a couple of people. This is done by a team, actually. So what kind of people or organizations make up the FutureTPM consortium?
Yeah, we have a very strong and friendly consortium. Our project includes 15 partners from 10 different European countries. We have 7 academics partners, I mean 7 universities, and we also have 4 large enterprise companies. Companies, I mean the unit of companies. And we have a number of SMEs. We have 4 SME partners, 4 the larger company partners, and 7 universities. That's not the only things I'm proud of. And we also have skills, experience, and in the different levels from those consulting partners, which are all key things for our projects. It's a balanced team.
And that's really the beauty of a project like this, is that you can bring in people from all different levels and you're all working towards a certain goal to get things done.
Exactly.
Tell me about challenges you've encountered. I mean, there's always some stories about things that were unexpected or events that happened. I mean, maybe in this case, it's, the COVID-19 pandemic just sort of put a stop to everything. Can you tell me what kind of challenges you encountered?
Like any other project, and our projects also face different challenges. And from my point of view, the challenge for our project are in 3 different aspects. The first one is a technical challenge, because this is a multitask research project. We need to consider the theoretical research and the practical research. So neither of them is easy. For example, a special anonymous digital signature schemes, which we call the quantum-resistant direct anonymous attestation, which is required for FutureTPM. By the way, the direct anonymous attestation, called the DAA, is a special crypto digital signatures, which was originally designed for TPM. So we need a quantum-resistant version, of course, but this is not existed before our project start. So we need to design by ourselves, and also we need to find practical with a good performance DAA schemes. So this is really a challenge, a technical challenge. There are many other technical challenges. Then the second aspect is about time challenge, because this project is in an early stage of post-quantum crypto researches. So many standard bodies, they have started to consider the standardization for post-quantum cryptography, but the standards for post-quantum crypto is not actually ready yet. So we need to synchronize our work with standard bodies such as NIST, ISO IEC, IETF, etc. So this time challenge is also what we have to face. So we needed to take the result from NIST. For example, we needed to justify our recommendations to the FutureTPM based on the NIST result. So this is about time challenge. And the last one, which probably many EU project is phase two, because European project in general is larger with a lot of partners, a lot of expertise. You mentioned the COVID-19. Yeah, COVID-19 certainly is a challenge, and we have to work online. But our research, our project work has never been stopped, slowed down because of COVID-19, and we just move all our meetings online. That's okay. And for resource management challenge, it's not only about moving our work from face-to-face meeting to online meeting. It's also we were challenged by the researchers' movement. Seems like a 3 years project is a bit long, and many key researchers during those 3 years, only now 2.5 years, they have changed their jobs, they move around. So some people are no longer be our official members during the project. So we have to, even our advisory board members, and some of them moved. So we have to keep their skills, their experience, and their contributions within the project. So we try to keep them as much as we possibly could. For example, if a person cannot be a project official member, then we invited them to be our advisory board member, and we still keep their contributions, their consultations in the group. I hope I answered your questions, because this question seems to have more things I can possibly cover.
Yeah, no, that was a great answer to the question. And I think it proves that maybe flexibility is the key to success when you're doing a large project like this, and a project that spans 3 years, for example. So, and it sounds like you've done that in FutureTPM, that you've been flexible and you took challenges as they came. And pretty amazing that you didn't have to slow anything down during the COVID-19 pandemic.
Yes, we have done our best, I believe.
I have one final question for you, Li, and that is, from a personal level, what does success look like for you in FutureTPM? So in other words, at the end of the project, what is it that will make you happy and sit back and say, wow, I've done everything I wanted to do with this project?
Yeah, for a success of a project, I think probably can see from different levels. As academic, and I would like to see the good publications for sure. And as a project, we also need to finish our target properly, like deliverables, the demonstrators, and we should do them in time, and also do them with a good quality. But I think for this particular project, because we try to create some solutions which can be used in the world, we try to recommend the right things to the FutureTPM as a real chip, a real technology. So I think a successful, from my point of view, is we also want to, this project, benefit the world. We want to end users where at the end to use our designed, developed, or recommended crypto algorithms. They will be included in the FutureTPM.
Okay, and that's a great goal. And it sounds like that's something that will be achieved. I must say, this is a project where most people listening maybe had no idea even existed, but you've done a great job in explaining how this works and what you're trying to do. So I say thank you for that. Also, thank you for your contribution to science, to making our world a better place. It's appreciated. Sometimes we don't see all the details of what you're doing, but we know that it works. So thanks for that. And finally, thank you for taking some of your time to explain to us how all of this works and what's important to you in this project.
Thank you. Thank you very much again for having me here. And I'm glad you make this broadcast and to let more people to know our project. And this is what we like the people to know. And also this is actually the researchers were very, very keen to make it good.
And good luck with the rest of the project. You have another few months here, and it sounds like everything is on track. So good luck finishing that out.
Yeah, thank you.
Okay, and we'll talk soon.
Thank you very much, Peter.
For more information about FutureTPM, visit futuretpm.eu. This podcast has been brought to you by Technicon. This project has received funding from the European Union's Horizon 2020 Research and Innovation Program under Grant Agreement number 779391.